So I'm going to go into the Biopac, and I can see that exercise begins at 19.6 seconds. So let's zoom back. Zoom back. Okay, so here's my begin exercise. So I'm going to auto scale my waves. And so before exercise, I need to know peak to peak. So I'm going to highlight this entire area right here. And I'm using the cursor tool to highlight, and I want channel 1 peak to peak. That is 1.32 liters per second. 1.32 liters per second. Now breathing rate. To do this, I need to calculate, figure out how many breaths it takes in a given amount of time, and then multiply that by 60 seconds over 1 minute. So looking at this airflow data before exercise, again, keep in mind this is flow, so this is a rate that oscillates above and below 0. So we're going to be considering absolute values as we go below 0, but 0 meaning that the rate has stopped. So this is, for example, the waves above 0 are exhales, and then it approaches 0 as you stop the exhale and begin the inhale. Similarly, the inhale dips down to here, and then as we approach 0, that's where the inhale stops and the exhale begins. So there's a small pause in between those two actions shown here where the rate in liters per second approaches 0. So just to highlight it and show you, that is one exhale, we get to 0 again, and then we have an inhale. So one up and down is one inhale, or rather one exhale and then inhale. So if I want one inhale and then one exhale, I can do that. So we want breathing rate. So again, we need breaths counted over delta T. So let's go ahead and just do, we'll start right here. So this is one inhale roughly, one exhale. Inhale, exhale, inhale, exhale. So I'm going to call this 1, 2, 3 total breaths. And now I want to see channel 1 delta T. How long does that take? And it takes 12.16 seconds. So I'm just going to go ahead and write that down here. 12.16 seconds for 1, 2, 3 breaths. Okay, so back to our equation, breaths counted over delta T times 60. So we're going to do 3 breaths in 12.16 seconds and multiply that by 60 seconds in 1 minute, and we get 14.8. So that's 14.8 breaths per minute. So before we multiplied by 60, if I divide by 60, this is breaths per second, and then the seconds cancels out as we multiply by 60 seconds over 1 minute. 60 over 1 is just 60, so I can multiply by 60, and this is breaths per minute. So that's that value. Our skin temperature will be relative, so this is 0 here. We need heart rate though. Okay, so our heart rate, we can go ahead and measure, and so if I just take this area right here, now I'm looking at channel, 41 mean, not channel 3 the mean. So channel 41 mean is going to take the average of all of these values shown here in blue. And that is 91.57. 91.57 beats per minute. So if you see BPM that typically stands for beats per minute, but be aware that it could be breaths per minute, so that's why I'm just typing all of this out. So again, relative skin temp is relative to the before exercise, so here it's going to be 0. So if it's positive, it has increased since exercise, and if it's negative, it has decreased. We need to measure mean arterial pressure using our systolic and our diastolic values here. So let's go to our equation. So what we're going to do is diastolic plus systolic minus diastolic divided by 3. So we're going to do all of these operations first and then add the diastolic value to that. So we have 113 minus 75 systolic minus diastolic equals 38 divided by 3, or times 1/3, is 12.67. Now we're going to add 75 to that. We get 87.67. 87.67, and this is millimeters of mercury, Hg. Okay, so that's before exercise. Now end of exercise, so that column out. Exercise ended at 320.7 seconds, so let's go over to that. 320.7 seconds. Auto scale. Okay, so now we need, what do we need? We need airflow peak to peak, but first let's fill this one out. So that's 320, I'm just going to do 320 seconds divided by 60 seconds in 1 minute. So that's 5.3 minutes. 5.3 minutes. Okay, airflow peak to peak. After exercise, I'm just going to highlight this region here, and I'm going to do channel 1 peak to peak, 3.1 liters per second. 3.1 liters per second. Breathing rate. Okay, so again, we need at least one complete set of inhale and exhale. So let's start right here, about 0. So we have 1 inhale, 1 exhale, 1 inhale, 1 exhale. And we'll go ahead and take that delta T value. We get 6.715. 6.72 seconds for 2 breaths. So now we're going to do 2 breaths divided by our delta T, which is 6.72 seconds, 0.29 or 0.30, whatever you want to do there. And we're going to multiply that by 60 seconds over 1 minute. We get 17.86. 17.86 breaths per minute. And you can see that the breathing rate has increased since we've ended exercising. Our airflow has increased since we ended exercising, so it seems like our data makes sense. Our calculations are making sense right here. I just want to go ahead and show you right now while we're at it, that if I just go to channel 2 delta T, notice that that is the same as channel 1 delta T. Any of these channels, delta T will be the same because they all share the y-axis with time in seconds, but their x-axes are completely different. You can notice that by just seeing the units, so liters per second, millivolts, degrees Fahrenheit, and beats per minute. But they all share time going this way, so we can plot them together like this, and the delta T values will always be the same. Okay, heart rate. So again, I'll just go in here, and I will go to my channel 41, my mean, 140.05 beats per minute. Let's see, how do I open that? Okay, that works. 140.05 beats per minute. And this is going over here. Okay, relative skin temperature. So this is at a point. So I'm going to go to channel 3, skin temp, and take the value here. So again, we want right at stop exercising. So that's this one right here. What is that value in skin temp? I'm going to say that is 90.1 degrees Fahrenheit. 90.1 degrees Fahrenheit. I'm going to record that down here because we need to see the change. So 90.1 degrees Fahrenheit after exercise. But then before exercise, we need to go all the way back to our beginning. So this is where exercise begins. We're going to highlight this region here. We'll go ahead and auto scale our waves. And I'm going to do delta 3, but I'm going to take the mean here instead of a value because I'm taking it over an area before an event instead of at an event. And so here it's 91.05. 91.05 degrees Fahrenheit before. So at the end, we had 90.1, so we're going to say 90.1 minus 91.05, and we get negative 0.95. Negative 0.95 degrees Fahrenheit. So what that means is that the skin temperature relative to before we began exercise was almost 1 degree Fahrenheit less at the skin surface after exercise ended, at the point that it ended. So now let's measure our mean arterial pressure, same way we just did it a few minutes ago. Excuse me. So systolic minus diastolic divided by 3. 152 minus 106 equals 46 divided by 3. And so that is our first part of the equation here. Now we need to add the diastolic value to that, which was 106. So 152 minus 106 equals. Okay, so now we need to calculate our mean arterial pressure here the same way we did just a few minutes ago. So systolic minus diastolic is going to be 152 minus 106. 152 minus 106. 46. Now we divide it by 3. We get 15.33. Now we need to add our diastolic value to that, and we get 121.33. 21.33 millimeters of mercury. 121.33 millimeters of mercury. Okay, now we can calculate our percent differences here. So airflow peak to peak. So percent difference is value minus reference over the reference times 100 to make it a percent. So it should always lean this way. You never want the same values to go this direction. You want a value minus a reference divided by a reference. So it's always going to tilt this way. So percent difference, and she's always going to give you a reference value. So pre-exercise is our reference. So pre is the ref, and our peak to peak there is 1.32. 1.32 liters per second. And then our post is our value, and that's going to be 3.1 liters per second. So now if we're going to do this percent difference, we're going to say the value minus the reference divided by the reference. So 3.1 minus 1.32 equals 1.78 divided by 1.32 is 1.35, we'll call it. Now we need to multiply that by 100, and we get our percent difference. So 135% is what I'm going to call that. And that's positive 135%. So to interpret your percent differences, our cutoff values are going to be at 0%. So I'm going to put that right here. 0% cutoff. And so what that means is that if it is less than 0%, it'll be negative, which means that your value is less than your reference value by a given percentage. If it is greater than 100%, like it is here, that means that your value is larger than your reference value. So if we look here, 3.1 is larger than 1.32, so that's why we get 135%. So this is actually, if you add the 100% of the reference value, this is roughly 2 1/3 times as much after exercise as before exercise. So just to show you that, I'll do 3.1 divided by 1.32, and we get roughly 2 1/3. So that is how many times larger this value is than that. And if you look here, it is 100% plus 135% to explain our percent difference here. So again, 0% is your cutoff, but whenever we go to this equation, we're going to have a different cutoff, but we need to fill this one out first. So maximum heart rate, let's just say you are 20 years old. So we'll say, we're going to use this equation here, so we're going to say 201 minus 0.7 times 20. Say you're 20 years old, and we're going to get a value here. So we need to do 20 times 0.7, we get 14. Now we need to say 201 minus 14. You get 187. So 187 beats per minute. Okay, so what percentage of this estimated maximum did your subject reach at the end of exercise? So again, this is over of, so what percent of the estimated maximum? So the of is the 187, so we're going to say that our max heart rate here, or that our heart rate for the is part of this is 140. So we're going to go 140 and divide that by 187, and then multiply that value times 100 to get a percent. So 140 divided by 187 gives us a value less than 1. We're going to multiply by 100 to make it a percent. We get roughly 75%. So 75%. So what that means, since it is less than 100%, that means that 140 is 75% of the maximum, which is 187. So if the value is greater than 100%, then the value that's in question, the heart rate after exercise, is greater than the max heart rate. If it is less than 100%, as in this case, then it is only a fraction, it's a portion of what can be reached at the maximum. So here we have a cutoff of 100% for greater than or less than a reference value, but down here in percent difference, our cutoff for larger or smaller regarding the reference value is going to be 0%. So just to explain what I discussed earlier about what a breath is regarding an inhale and an exhale on your airflow, it's a little bit easier to see in the pulmonary lab where we had volume in liters increasing with an inhale and then decreasing with an exhale. But regarding our flow, our 0 is where the air is not moving anymore. So liters per second. So this is a rate. So we can see that after we inhale, we stop for a minute and we begin the exhale process. So here we hit 0 liters per second. So as you switch between the actions of inhaling and exhaling, or inspiring and expiring, we approach 0 as our rate for liters per second. So that's why we have one wave for one breath here, but we have 2 waves, if you want to call it that, regarding our flow compared to our liters. So again, as we inhale, the flow starts from 0, goes down, and then approaches 0 again, and then as we begin the exhale, the rate increases and then approaches 0 again as we begin another inhale.